previous lecture, we have discussed the basic concepts of pipeline and parallel processor. We have discussed the segment architecture of implementing a pipeline by taking one example. So now today we will discuss the general considerations, that means why we implement the pipeline organization. So pipeline is efficient in those applications that need to repeat the same task many times with different set of data. That means we pipeline structure is very difficult to set up. So generally we use the pipeline in that applications where we have to perform the same task number of times using different sets of data. For example, example, in the previous example, we have discussed this segment architecture of pipeline. Here, there was three pipeline segments. This is first pipeline segment, and this is second pipeline segment, and this is third pipeline segment. Okay, here you can see the value of A, B, C ranges from 1 to 7. Okay, so its value ranges from 1 to 7. That means these operations are to be performed when the value of I will be 1 and up to the value of I equal to 7. That means same instruction has to be executed 7 times. Okay, so we usually implemented the pipeline in that applications that need to repeat the same task number of times with a different set of data. So next I'm going to discuss the advantage, or you can say general consideration, for the pipeline organization. So first is speed up. It is a quantity that serves as an indication of the efficiency of a pipeline. That means speed up is like a performance metric that measures the efficiency of the pipeline system. It is a measure of number of clock cycles that are used to perform a single task. Next is speed up ratio. Speed up ratio and speed up both are the metrics that are closely related to each other. Speed up ratio is a measure of performance of two systems processing the same problem. That means whenever we have to execute the same problem using non-pipeline system and using the pipeline system, it is a ratio of that both systems. In the context of pipelining, speed up ratio measures the performance of a pipeline system in contrast to a non-pipeline one. So last is throughput. Throughput is a number of executed instructions in the system per second. Now here we will discuss speed up in detail. Consider an example where k segment pipeline with the clock cycle time TP is used to execute n tasks. Okay, so here number of tasks are equal to n and the segment that are used in pipeline is equal to k, and the clock cycle used to perform the task is TP. Okay, so the first task require time k into TP. Now what is k here? K is a number of segments in the pipeline architecture. Okay, so the first task require k into TP. Now the first task require time k into TP to complete its operation because there are k segments in the pipeline. Now how many tasks are left behind when first task is already executed? The number of tasks was n. Okay, so one task has been executed and n minus 1 tasks are left. Okay, so the remaining n minus 1 task emerge from the pipeline at the rate of 1 per clock cycle, and they will be completed after time equal to n minus 1 into TP. Okay, now why here it is n minus 1? Because one task has already executed and that is taking time k into TP. Okay, so rest of the task will take time n minus 1 into TP, and TP here is the clock cycle time that will be required by every task for its execution. So completion of n task in a k segment pipeline requires k plus n minus 1 clock cycles. Time k into TP. Second task n minus 1 into TP. Okay, so TP will be common and the time taken for completion of n task will be k plus n minus 1. Okay, so here the completion of n task in a k segment pipeline require k plus n minus 1 into TP is clock cycle. One example, speed up. How we can calculate the speed up? Okay, in our current example, the time required to complete all operations is 3 plus 7 minus 1 equals to 9 clock cycle. Okay, so now we have taken one example in the previous lecture where there was 3 segments, okay, and the number of tasks were 7 because I value range from the value of I ranges from 1 to 7. That means we had to perform the 7 tasks using the 3 segment pipeline. Okay, so now according to the speed up formula, how we can calculate the number of clock cycles required to perform that 7 tasks. Okay, so here the formula was k plus n minus 1. Okay, so here you can see that 3 is what? 3 is a number of segments. So k will be equal to 3 here plus n minus 1. Now what is n in the previous example? There were 7 tasks. So it is 7 minus 1. Okay. So it is 3 plus 6. So total 9 clock cycles will be required to perform the 7 tasks. Okay. But if what happen if we do the same thing by using non-pipeline structure? In that case, n into number of segments. Okay, so n was 7 and k is equal to 3. So there were 21 clock cycles required to execute all that 7 tasks. The speed up, so that are too much as compared to the pipelined structure. Okay, the clock cycles in the non-pipeline structure are 21, while in the pipeline organization, while using the pipeline organization, the clock cycles required to perform the same number of tasks is only 9. Okay, so this is the difference between the speed up metrics while using pipeline and non-pipeline system. Speed up ratio. So how we will calculate the speed up ratio? Okay, speed up ratio is closely related to the speed up. Speed up of a pipeline processor over an equivalent non-pipeline processor is defined by the ratio. Speed up ratio is basically used to measure the performance of the pipeline system. Is calculated by dividing the speed up of non-pipeline system and pipeline system. Okay, so this is the speed up of non-pipeline system and this is the speed up of pipeline system. Okay, where n into tn is the total time required by a non-pipeline unit to complete n task. So next, this is speed up ratio as the number of tasks increase. That means when n becomes larger than k minus 1 and k plus n minus 1 approaches the value of n. Okay, so now let's see the previous slide. In this slide, the speed up ratio was equal to n into tn. Okay, it was equal to n into tn. That is the time taken by the non-pipeline processor, nk plus n minus 1 into tp. Okay, here n stands for non-pipeline, p stands for pipeline. Okay, time taken by pipeline is denoted by tp, time taken by non-pipeline system is denoted by tn. Okay, so here when the number of tasks become large, okay, that means when n approaches to k plus n minus 1, what happens? Under this condition, the speed up will become, if we put k plus n minus 1 equal to n. Okay, so what will happen in the previous equation? The previous equation was n into tn upon k plus n minus 1 into tp. Okay, so when n becomes very large and it approaches k plus n minus 1. Okay, in that case, k plus n minus 1 equal to will be equal to n. So n tn upon n tp. Okay, n will cancel and the speed up ratio will become tn divided by tp. If we assume that the time it takes to process a task is the same in the pipeline and non-pipeline circuit, we will have tn equal to ktp. Speed up then becomes s equals to k. Okay, this shows that maximum theoretical speed up that a pipeline can provide. Here s is the speed up. Okay, so speed up can provide is equal to the number of segments in the pipeline. K is the number of segments here. Okay.